Okay, so in the last class we had discussed agent design, you see, and we had discussed the various parameters or attributes of environments. We talked about different types of agents and so on. So we'll be getting into that a little later, but okay. So last time we saw that we need to sort of learn some tools before we can start doing design, right? And for that, also to get you started with the actual practical stuff, we are going to look at the deductive part first. Okay, then in the second half we'll look at the inductive part, that is essentially how you can infer something from data, right? So right now we are assuming that we understand the task domain and we try to work in the task domain. And one of the tools that we are going to use here is basically logic, and in particular logic programming. We'll see several examples of how logic programming can be used to describe task domains and to solve problems in different task domains. Okay, so let's start with this today. This will also help you to learn Prolog, which is the sort of major logic programming language, right? So this logic programming is also sometimes called relational programming, and it's a very different style of programming in the sense that it's a declarative programming approach, uh, distinct from what you have been used to. So whether it is Python or C, all of these languages, C, all of you have learned, that's a procedural programming language where you actually write sequence of statements and functions, and each function consists of sequence of statements in C, for example, and you start with the main program and it executes a sequence of statements one after another, right? So there's a clear description of what is to be done. So it will say start main program, execute first statement, then execute second statement, and so on. So it's a procedure, right? In contrast, logic programming is declarative. So when we say something is declarative, what we mean is we are going to state facts about the world, right? We are going to state facts and rules about the world. We are not going to say do this, then do that, then after that do something else, and so on. We're just going to state facts and rules about the world, and then we are going to try and reason out, uh, answers, whatever is to be done, for example. So this may sound a little odd at first, but you will see as we go along exactly what it means. Okay, so this whole style of programming started in around 1970, and this language called Prolog was invented in 1771 by this French computer scientist called Alain Colmar and Philippe Roussel, right? And some contributions were also made by Robert Kowalski, who was in England at that time. The other two were in France. So by 1972, initial implementation of Prolog was available. The logic that is implemented in Prolog is called horn clauses or horn logic. We'll look at the theory of this briefly a little later. I'm assuming most of you have done logic, in perhaps the discrete math course or otherwise. If you have not done it, that's why we'll review it briefly a little later. Some of you may not have done it. Now, Prolog is Turing, which means that anything that you can do in any other programming language, you can do in Prolog. But its real use, as you know, all programming languages have certain domains in which for which they are most suited. So in particular, Prolog is best suited for heuristic search, theorem proving, rule-based systems, planning, NLP, okay, and so on. So by NLP here I mean you want to process language. I don't mean you want to learn anything. So that's the inductive part, which, as I said, we'll be doing in the second half. Now, it is not a very widely known or used language in industry, but it is used in several niche applications and perhaps can be used in many other applications very effectively, but is not, because many people don't know it. It's not a popular language, right? But it's a very powerful language in terms of a declarative style of programming, and in particular for AI applications, it turns out to be a good language to use, because you want to manipulate, very often you want to manipulate symbols here, because you want to represent the problem domain in terms of certain representations and then manipulate those representations to get answers. Okay? So it turns out to be a good vehicle for that. Now, I hope all of you you should download SWI Prolog. So let me, I put that on the, okay, this called SWI Prolog, and this is free, and it is a mature implementation. It has been around for many years, and it runs on all the platforms. It runs on Unix-like platforms. It runs on, of course, Windows and on the Mac. So those of you, irrespective of what kind of OS you are running on your laptop or your desktop, this should work. Okay, so download it from the Prolog, SWI Prolog site. The link is present in the course website, and get it running. So we will be using it today for examples. Okay. All right. So a little bit about Prolog before we actually get to the examples, and examples will make everything clearer. So Prolog has just a single data type, which is called a term. Okay, and this term can be either atomic, that is, it's called an atom, or a constant, or it's also called a constant. An atom can be a constant, or it can be a compound term, or it can be a number or a variable. These are atoms also, but they behave slightly differently. So numbers are atoms, simple strings are atoms, simple sequence of characters starting with a small letter are atoms, and so on. So if you look at the second point, it says that beginning with small letters, right? So here are examples of atoms. So Z is an atom, blue is an atom, this is a string, but this is also an atom, but once you make it a string, this can be capitalized. If you have only a sequence of characters, then it must start with a small letter. Okay. If it is a string, any string is also an atom. Right? It should begin with small letters if it is not a string. Now, numbers are also terms. They are also, in some sense, you can think of them as atomic. And they can be either integers or they can be floating point numbers. Right? Variables are also terms. Variables again are sequences of characters which must start with a capital letter, as distinct from atoms, where these atoms are things which must start with a small letter. Variables must start with a capital letter, or they can start with an underscore. Okay, underscore is also a variable by itself. And it can start with an underscore or a capital letter. Right? Other than that, subsequent characters can be numerals and underscore, etc. So you can create So for example, X, capital X is a variable. This is also a variable. Okay. It starts with a capital T, it has other letters in it. There can be numerals in it also, and there can be underscores. If you have something like this is also a variable. Okay, which starts with an underscore. So this will be a variable, and small also will be a variable because it's starting with an underscore. It's not a dash, it's an underscore. Now you can have compound terms or structures. They allow you to have what are called functors here. Okay. So here we had just sequences like Z, blue, etc. They are at atomic, they are constants. Here, for example, we have compound structures. So this can be, so you can think of them as a functor with arguments. Okay, and these arguments themselves are terms. So basically, what we are talking about is if you look at a compound term. Okay, so we said you have term. We'll see a chart shortly. So these can be atoms, or that is simple ones. These can be compound. Everything is a term, right? So now we are looking at this compound. So compound starts with something we call a functor, okay, which must start with again a. So it's a constant. It's an atom. So this itself must start with a small letter, and then there are arguments here. The arguments, let's write them like this with angular brackets. So this is a sequence of arguments separated by commas, and each argument in turn is a term. Okay, so it's recursively defined. So a term is an atom or a compound, and each compound must have a functor with arguments, where each argument in turn is also a term. So which means you can nest it to any level. So strings you have seen, they are also basically terms, atomic terms. So strings are a sequence of characters beginning and ending with quotes. They can either be single quotes or double quotes. And finally, you have something called a list, which is very useful in Prolog to store sequences of things. So a list is simply an ordered collection of terms put within square brackets. So this is, for example, a list which contains a number, integer 2, it contains the atom A, it contains a string which is a list, which is itself also an atomic thing. So these are the kind of data types that you have in Prolog. So basically all of these are terms, and terms are, as because we saw, can be atomic or compound. And if I go to this thing, so this is what is a term. All data objects. So they can be simple objects, which can be constants or variables, or they can be, these are often called structures. These are your compound things. So they are, so this compound we saw is basically a functor followed by, within brackets, the arguments. And each argument in turn can be a term. Simple objects can be variables or constants. Constants in turn can be the simple atoms we saw, or they can be atomic numbers, right? Numbers, that is integers or floating point values. So these are basic data types that are available. So you may think that they are not very complex or complicated. For example, when you compare it with some languages which allow objects and so on, there are extensions of Prolog where objects are allowed, but we are not going to bother about it. But for symbolic manipulation, this is good enough. And we'll see when we actually tackle some problems, we will see that this actually works quite well. Okay, so now Prolog programs, how do they look? Prolog programs are made up of facts and rules. Okay, so remember, all of this is coming from logic. So a fact is a statement that is asserted to be true, represented as a predicate about constants. So for example, what you see here in uh, typewriter font, male Rahim, right? Notice the small characters which start the uh, predicate, and the constant here, Rahim, starts with a small r. So what this is asserting or saying is true, saying that this is true, that is Rahim is a male. Here is another example, it's saying female Sita. So what this is asserting is that Sita, the constant Sita, is a female. Okay. Now here is a predicate with two arguments. So it is saying parent Sita Rahim. So what it is saying is that Sita is a parent of Rahim. Okay. And this is saying Rahim's age is 10 years. One assumes is 10 years. Okay. Here is a predicate with three arguments. So this is saying that the first argument, namely 2, is between 1 and 3. So more generally, it could be other constants. So it could be 3 is between 4 and 5, or 3 is between 4 is between 3 and 5, or 4 is between 3 and 10. Anything of that kind. So you can instantiate this with any kind of constant, but the assumption is that whatever you are stating here is true. Okay? You are stating true facts. Note that you have to put a full stop at the end. Okay? I'll see actual code in a minute. So those are facts. So you are asserting something. The second form, which actually is the one which allows you to do actual interesting calculations, is a rule. Okay? And what is the rule saying? A rule is something which looks like this. It has a head and it has a body with this as this colon dash, colon followed by a dash as an implication symbol, right? You have to read it in the reverse direction. So the body, the head is a simple predicate, is just a predicate with arguments. The body is a conjunction of predicates on the right hand side, usually separated by commas. And what the whole rule is saying is that if the body is true, then the head. It's actually giving you an implication. It is saying if body, then head. So it's saying that if the body is true, then the head must follow. The head must be true. We'll look at examples of this, many more examples of this as we look at the code. Okay, so that's what it is saying. So here is an example. So if you want to code the rule that if x is human, then x is mortal, you can write it as human x. Notice now that here we are having a variable, it's capital X. So what you are saying is that human x implies x is mortal, or equivalently, if it is true that x is a human, then x is mortal. Okay, it has to be read from right to left. The condition is on the right, and the head is a single predicate, mortal, and it is asserting something about the arguments. Right? Here we have got a very simple rule. We'll see more complex rules as we go along. So note here that x is a variable. So in a rule, mostly you are asserting things about universals. That is, what you are really saying is that for all x, if x is human, then x is mortal. So you are doing some kind of universal quantification, writing this for all x. Okay, so basically what you do is you model the domain in terms of facts and rules. We'll come to an example shortly. You model the domain in terms of facts and rules, and when you want to do a task, you basically have to execute a Prolog program. To execute a Prolog program, so this when you write a Prolog program, the program itself is simply a model of the task domain. Okay. When you want to do a specific task, then you have to have a question or a goal. Some people call it a question or a query or a goal. Right? All these three terms are used in the Prolog literature. A goal is probably the most common one. So you have a goal. Now the goal is something that you need to prove to be true. Okay? So a goal is a predicate. Usually it can be a single predicate or it can be a conjunction of predicates. Typically with arguments, at least some of which are variables. Okay? And what the Prolog program tries to do during execution is it tries to find bindings for the variables. So if something is a variable, it is must have a value, right, ultimately. So we'll try to find values for those variables such that the goal is true. Right? So if it's a single predicate, it will find bindings for the variable arguments such that the goal is true. Okay. If there are multiple predicates, then it will try to find a binding for each of those variables in each of the predicates, so that in conjunction they are true. So the first predicate must be true, then the second predicate is true, third predicate is true, and so on, if there are multiple predicates in the goal. And this process of trying to prove this, right? You are trying to prove that the goal is true. In the process of trying to prove that the goal is true, you are going to instantiate the variables, which means you are going to find values for those variables such that the predicate or the goal more generally is true, because the predicate, the goal can be a conjunction of predicates. It will not be just a single predicate, so that the goal is true. And how does this happen? It actually happens through a theorem proving process. The theorem prover implemented in Prolog is called SLD, for Selective Linear Definite Resolution. We'll, as I said, look at this theoretical part a little later. It's more important that you understand how to work with it. And this happens automatically, right? We will actually look at how exactly execution proceeds, but this is exactly what happens. And the the result is either it comes out and says false, which means it cannot prove that the goals, it cannot find bindings for the variables which will make the goal true, or it will come out with a set of bindings which will make the goal true, right? And the interesting thing about Prolog is it is possible that there will be multiple different bindings which make the goal true, right? Again, we'll see examples of that shortly. And you can ask the Prolog interpreter to find all the bindings. Okay? And you can ask it to find all the bindings in one shot, so you get all the correct answers, or you can ask it to find them one by one. That is, you control it. So you ask for the first binding, it will give you the first answer, then you ask for the next binding, it will give you the next answer, until all of them have been found, or you can exit at any point. Okay, so at this point, let us switch to actual examples. Okay, so I have a Prolog program here, and where is this so that you can see this? Okay, so notice that this part where I am in a terminal, I am going to start the Prolog interpreter by SWIPL. Okay, I am using a Linux machine. I've downloaded and installed SWI Prolog on my machine. So this does not have a GUI interface. Well, some on Windows I think you may be able to get a GUI interface, or there may be some plugins which allow you. But for our purposes, we will use an editor here, where we'll write a program, and we'll use. So if I do this, you can see that I have an interpreter which starts with a question mark, right? So the question mark is all the time it will asking for a goal. Okay? So first I'm going to load this program which is called relations. So here is the file relations1.pl. So the current directory is where I've stored this file. Okay? And you can see that. So for example, if I actually do ls, you can see that I have this file called relations1.pl, relns1.pl. So now I will read this program into my interpreter. There are multiple ways to do it. One simple way is just to give a square bracket, give the name of the file. The extension is assumed to be .pl. Put a dot at the end. So every time you have to put a dot at the end. And so what this means is that it has read in the program. Okay, it has read in this whole program. And now let us look at this program. Okay, so so in this program I am actually asserting certain facts. So I am saying male Ram, male Rahim, male Shyam, male Ravi, and so on. Male Raj, Geeta is a female, Anita is a female, Smita is a female, Sita is a female, Sudha is a female. Then I am giving some parent-child relationships. Right? Notice that I can write it in multiple ways. I can what I am saying here as a fact is that Ram is the parent of Rahim. Okay, so here it's telling you the meaning, what this means, and I'm asserting that this is a fact. Similarly, I'm saying Geeta is a parent of Rahim. Okay, and similarly for some others that we have given there. Okay, Shyam and Raj. So Shyam is the parent of Raj, Anita is the parent of Raj, and so on and so forth. Okay. Now let's come to the rules. Now you could have asserted some of these things directly. For example, instead of now, this is to give you examples of rules and also examples of how you can. So this could be a domain where you are storing all your ancestral information. Okay, and you want to know who's. I mean, as we will see, we can get all kinds of information from here, right? So, so the rules are going to define various things like father. So now you can see, what is this saying? This is saying that X is the father of Y. That is what father here, the predicate means. If the following is true, X is a parent of Y and X is male. Right? We know that a father is the male parent, and that's exactly what we are asserting here. So the body of this rule says that if X is the parent of Y and X is male, then we can say that X is the father of Y. Okay. Similarly, mother is the same thing. X is the parent of Y, but now X is female. So in that, if this is true, then X is the mother of Y. Now notice this sibling. So what is sibling? Sibling means they are either brothers or sisters, and X and Y have to be distinct, right? So X and Y have to be distinct, and they must have a common father and a common mother, right? Notice we are also defining step sibling. Okay, so sibling is so X and Y are siblings if X has father, Z is the father of X and Z is also the father of Y, W is the mother of X and W is also the mother of Y, and X and Y are not equal, right? Because this will be satisfied if I make X and Y equal. Notice that they are variables. Okay, so if I am the only child of, let's say, somebody, then X can be instantiated to me, Y can also be instantiated to me, and then I'll say that sibling X and Y will be true. However, we know that, you know, when you say somebody is somebody's sibling, it means that I am not my own sibling, right? We understand that. But here you obviously have to state it explicitly. So sibling means they have the same father and mother, and of course X and Y are distinct, and so that X is not equal to Y. That's so if all the right hand side predicates are true, notice this is written in the infix format. Otherwise, it's usually written in the prefix format. So because you have father, I mean, this is the predicate and then your arguments. So here, yes, each of these has to be true. Then we can claim that X and Y are siblings. So now look at step sibling. So notice that how I'm building things up. So I defined what a father was, I defined what a mother was, then I defined sibling in terms of father and mother. Now step sibling. So X and Y would be step siblings if basically they have a father in common and of course they are distinct, right? Or they have a mother in common and they are distinct. So now notice we have two rules. So we are saying that step sibling X and Y are step siblings if Z is the father of X and Z is the father of Y. Is there a question? Yeah, we'll see that in a moment, why it will, how it will work. So right now, yes, you're right. Step sibling will, the question is all the things on the right hand side have to be true, right? So we will see later on that if as things stand, they are uh, we have defined step siblings not completely, and we'll see later on how you can define that. For example, you can say the mother of X and Y should be distinct, right? So you can say mother of X should be, say, W, mother of Y should be something else, say V, and W is not equal to V. Right? Right now we are not defining it that way, but you can add that and you can define it that way. Right now we are not doing it, and I will come to the reason why we are not doing it shortly. But you are right. If a step sibling, if somebody is a step sibling, or rather, if somebody is a sibling, it will also imply that the persons are step siblings as it stands, right? Because the first part is the same. The mother part is different, but we can add that. That's not a problem. So if you can add that, you can say mother W of X, mother, let's say V of Y, and W is not equal to V and X is not equal to Y. Okay, that's what I'm saying. We can say that. And of course, we'll have to say the same thing here. For step sibling, I'll again have to say the same thing with father. Okay, so I'll say father W X, father V Y, and W is not equal to V and X is not equal to Y. Okay, yeah, this would be more accurate, but what I did earlier would work in most cases because of something that we'll see later. Okay, so now you can define similarly brother, sister, and so on simply by using the earlier one. Brother is when X and Y are siblings, and X is male. Sister is, so X is a sister of Y, so you're saying sibling XY and X is female. Okay? So here order is important clearly. X is the sister of Y. So Y could be male or female, we don't care, but X has to be female. Similarly, step brother is similar. They are step siblings. X is male, step sister is similar. Okay. Now we want to define an interesting relation, which is basically the ancestor relation. Right? You have, let's say, these ancestral trees, and you want to actually look at that and ask. You can define other things later on. we can define other things later on. So since we have changed the program, we'll have to reread it. But other ones are obvious, right? So now ancestor. Now notice how ancestor is defined. Ancestor is being defined by saying that X is an ancestor of Y if X is a parent of Y. So your parents are clearly your ancestors. But ancestor is a sort of transitive relation, right? So you're saying that X is an ancestor of Y if Z is a parent of Y, okay, and X is an ancestor of Z, right? So that's what we are saying here. And now similarly, so you're saying that you should have Y's parent Z, X should be ancestor of Z, then X is an ancestor of Y. So if you kind of look at it from a diagrammatic point of view, let us create some. So what we are saying is that, let's say you have X here and you have such relations here. So you want to check whether you want to say that X is an ancestor of Y. Okay. Ancestor of Y. So what you're saying is, say Y is somewhere here, immediately you have Z like this, and now X, and there are in between things, so this is again an ancestor relation, right? So X is an ancestor of Z, this is an ancestor relation, and this is a direct thing, so it's a parent relation. So if this is true, then you have ancestor. Of course, note that other one will also be true. That is, namely, if you have X here and you have somebody here, so X is a parent of this, and then this person is an ancestor of Y. Okay, so if you have Z here, so you can have that ancestor X is an ancestor of Y if X is a parent of Z, parent X Z, and Z is an ancestor of Y. Ancestor Z Y. This will also work, right? Okay, so to kind of look at this thing, let us do one more thing. Okay, so what I'm trying to do now is to basically draw the ancestral tree. Okay, so what is happening here? Let's look at the facts. So Ram is a male, Rahim is male, etc. Then come to the parent relations here. Okay, I am highlighting them in blue. So if you look at these relations, I hope I've captured all the relations. Yeah, all the facts. So let's try to do this. So Ram and Geeta are Rahim's parents. So let us try to see how it looks. So Rahim, and we have Ram and Geeta. Okay, the first two are there. Then we have Shyam and Anita are Raj's parents. So let's just put something here, Raj, Shyam and Anita. Then the second, third and fourth. Then we are seeing that Ravi is Smita's parent and Sita is Geeta's parent. Okay. So we have yet another relation. So Sita is Geeta's parent, so we have Sita coming here. and we have Sita is also Anita's parent, so this Sita is Anita's parent, okay, and Ravi is Smita's parent. So let's do this. We're looking at this now. So Ravi is Smita's parent. So Smita has to be added somewhere. Let's add it. Let's add it here. And we have Ravi. Okay. So we have already done Sita is Gita's parent and Sita is Anita's parent. We have done that. Smita is Sudha's parent and Ravi is also Sudha's parent. Okay, Smita is Sudha's parent and Ravi is also Sudha's parent. So this is the kind of structure we have, right? From the given facts, this is what we are getting. Now you can see various things here, right? When we draw it as an ancestral tree, you can see these relationships. You can see that Sita is a grandmother of Rahim. Similarly, Anita is a mother of Raj. Shyam is the father of Raj. Sita is also a grandmother of Raj, and so on, right? Ravi is, have I missed anything? Ravi is parent of Sita and Sudha. So, yeah, looks like I have got all of them. Parent relationships. Yeah, just a moment. I'll have to. Yeah. Parent Anita Smita. You have it. Okay, let me check. Yes, you're right. Yes. So, yeah, I added that now. So you see some things, right? For example, we have not defined, for example, something like separation or divorce. But looking at this tree, you clearly see that something of that kind must have happened. Because Smita is, Ravi is a parent of Smita and Sudha also. Of course, we don't know whether Anita is a parent of Sudha or not. But if it's not given, we cannot assume anything. So we have no way to know. If unless Anita is a parent of Sudha, Ravi and Anita may have been divorced. Right? So Ravi has some other. So Sudha has some other mother. Well, Sudha actually has Smita as the mother. Right. So you have this rather complex or interesting relationship. So you can conclude that Ravi and Anita must have been sort of separated. There has been some separation at some point, depending on how it went. So from here you can get various kinds of relationships, right? So you can get step sibling relationships, step brother, step sister relationships, you can get grandmother relationships. And imagine now doing this for your entire family tree. So if you have, for example, DNA information trees, you remember, I mean, you probably know that DNA allows you to build the tree of life or the tree of humanity, for instance. And you can try to build such very complex trees. So you could, in principle, convert them into facts and rules like this, and ask, okay, is there a single ancestor? In this case, for example, we can't say because there are multiple people who don't have any ancestors. So you have multiple, I mean, only if there's a single root from which everything descends, you will have a single ancestor. But here Ram is there, Sita is there, similarly Ravi and Shyam are there, and we don't know where they go. So in this case, they are not really. I mean, it's a graph really. It's not a simple tree. So, but this is interesting. So now let's see what happens. We'll read it in again. So another way to read it is using the consult predicate. This is a built-in predicate, and you can do the same thing. Let us save it. Okay, I've saved the file, and now okay, so it's read it in with the new thing, that is that we changed the step sibling thing, right? Now, so what has happened is that now you can actually list things here. So you can say listing and give a predicate, say I say parent. So it will tell you all the facts and rules relating to parent. Okay, similarly, let me say listing, and I say, I don't know, say step brother. So it gives you the step brother thing, right? It's saying step brother is if it's a step sibling, and so similarly, if you say listing step sibling, it will give you the corresponding roots. And misspelled sibling, so that's why you got that. So you can now see the two rules for step sibling that we wrote, right? Now you can, so this is the program, okay? It has facts and rules. Now you can try to write some goals. For example, we can write some very simple goals like so I can say female Anita, right? Now this is actually a fact. So it's going to check your set of facts and say whether it's true or not. Right? So female Anita is true. I look at say female someone else. This I have not asserted this in the database, right? So Sanita is just not present anywhere. So if I say this, so you will say that it says it is false. Okay. So basically this fact is not true. So what it does when I say female Anita, or more generally, now let's look at if I say female X. Now X is a variable. So now when I hit enter, it actually, you can see, goes and matches with this, right? It goes and matches with this. So now notice there are multiple other, so this is the so-called binding, right? This X is now bound to this value. You can see this is often called a substitution. If I substitute X with Geeta, this becomes female Geeta, and it actually is true, right? Because it matches with this female Geeta here. I can now give a semicolon, and it will give you the next answer. It says, well, if X was substituted with Anita, then also this is true. Then give me yet another answer. I can keep us answers by hitting semicolon. So now X equal to Smita also makes female X true. Notice that X is a variable. It can be instantiated in multiple ways to make it true, and essentially all the facts where we have said female somebody, all those instantiations will make it true, right? So in particular, apart from Smita, Sita is there, and then Sudha is also there. And then notice that it stops because it has given me all the possible answers. Okay. Now let us look at something else. So you can say, for example, mother X Y. Okay. So if you now look at this graph here. Okay, if you see this, so you have a lot of mother relationships, right? Sita is the mother of Gita, Gita is the mother of Rahim, Sita is the mother of Anita, Anita is the mother of Raj, Anita is the mother of Smita, Smita is the mother of Sudha, right? All of these instantiations will give you the make the mother relation true. And we can ask now this. For example, now if I say this, it's giving me a binding for X and Y, which makes it true. So notice it's given me Gita Rahim as the first binding. Now I can ask for the next binding. So now it is giving me Anita and Raj. Right? So it's giving Anita here and Raj. Next, Anita and Smita. Next, Sita and Gita. So now it's gone up, Sita and Gita. And we'll see exactly why these are coming in this particular order. We will see later on when we describe the procedural meaning of this program. I mean, clearly the declarative meaning is that it should be true. The order doesn't matter, nothing matters. But clearly if it has to go and prove theorems, for example, if it has to prove the condition, then it has to pick up a predicate and show that it is true. So if it has to do that, then it has to do it in some way, right? It can pick up the predicates randomly, it can go from left to right, or it can go from right to left. But it has to pick them up one by one and show that they are true. So the ordering and how it does that picking up matters, right? So the answers will change, or rather the answers are dictated by that order. So that's in some sense the procedural part of it, which is not really the meaning of the program. The ordering actually doesn't matter so far as the declarative meaning is concerned. Okay, so Sita Gita, then we have Sita Anita, we have Smita and Sudha. I guess that's all. Yeah. So then it's done, right? So you can see this. So similarly, you can try to check, for example, step. What do we have here? Well, just let's try step sibling. So Smita and Sudha are step siblings because they share the same father. Right? We don't have any mother defined for Sudha. Obviously, she probably has to have a mother, but in our database there is no mother. So simply by having the same father, by virtue of having the same father, Smita and Sudha are step siblings. Then Sudha and Smita, it's doing the same thing but in the reverse direction, you can see. Then it says Raj and Smita are step siblings because they share a mother, Anita. Okay. Now you'll get the other way around, Smita and Raj. So how to stop this we can see, because so far as the program is concerned, it is perfectly right, because X, all we are saying is that X and Y should be not the same. So if X is Smita, Y is Sudha, of course they are not the same. And similarly, if Y is Smita and X is Sudha, again they are not the same. So it's giving you both the answers, however both the answers happen to be in this case the same. Same thing is happening again with Raj and Smita. Okay, those are the only step siblings you have. Similarly, you can now ask for whatever, we know that grandmother. Now, not everything needs to be a variable. So, for example, Sita we saw, if we look at this thing, Sita is, a grandmother for several people. So, we can try to see that grandmother Sita, and now we say X here. So Sita is a grandmother of Rahim, you can see that. Similarly, now Sita is a grandmother of Raj, because Anita is Raj's mother, Sita is Anita's mother, and X is Smita. So she is also a grandmother of Smita, right? Because Raj and Smita are are step siblings, and so she's the grandmother of both of them. Similarly, you can now add things, right? You can add things here. I have added a few. You can add things. Now notice that you can try to do things differently. You can define, if you want, for example, child of yx is the same as parent of xy. You can ask for grandchild of, great grandchild of, and so on and so forth. Okay? Similarly, one can define a successor relation, which is the sort of inverse of the ancestor relation. So X is a successor of Z if Z is an ancestor of X. So you can now define a large number of possibilities here. So you can see that here is a domain, let's say domain of ancestral relations or tree-like relations, or rather you can say hierarchical graphs basically, where you have hierarchies with no cycles. I mean, in the sense that these are directed graphs, so we are saying that if you have a parent relation, then you basically have an arrow from the father or mother to the child. Okay, that's how we have represented it. So you can imagine now that many kinds of things can be, many domains can have information of this kind, where the relation is not necessarily the parent, but it's really a directed acyclic graph, right? So directed acyclic graph. If you want these successor, ancestor, and various other kinds of relations, you can find them. For example, you may want to know, for example, for complex sort of assemblies, say a car. Okay? A car consists of thousands of parts, right? And so a car can be made up of the body, then the engine. So it consists of a lot of sub-assemblies. Sub-assemblies in turn consists of further sub-assemblies until you come to the the basic part. So you may want to actually create a system where these things can be written as directed acyclic graphs, right? So car can consist of a large number of parts. So think of them as their children, sub-assemblies. Each sub-assembly can have further sub-assemblies until you come to the basic part. So the entire car or any object which is complex for manufacture can be modeled like this, right? And you can then ask a variety of questions about which assemblies are present. I mean, you can actually do a full-fledged that is, you can query it in various ways to answer questions, right? So it's a structural. It gives you a structural view of a car. If you want, you can use it also for doing inventory management. You have enough parts. So what I'm trying to say is that this is actually quite powerful. This whole business. What we have done here is we have created a model using Prolog for really a directed acyclic graph. So for any problem domain which can be modeled via a directed acyclic graph, this becomes a very powerful way of modeling it. And then you can ask, a lot of queries can be there, right? Which can be answered. So if you're making a large number of cars, different cars, and some of them share sub-assemblies, then all of those things get easily modeled at this, right? If you model it as a directed acyclic graph, and you can easily create lots of queries that managers may want to ask can become simple goals in Prolog. So here we were looking at just simple single predicate goals, but you can have goals which have multiple predicates also on the right hand side. So for example, let us say mother x y and mother, so x is the mother of y and y is the mother of z. Okay, so now you're getting this relation Anita, Smita, Sudha. So for example, Anita, Smita, Sudha. Anita is the mother of Smita, Smita is the mother of Sudha, right? You're getting this relation. So basically, this is another way to write Anita is the grandmother of Smita. Okay. Right. So now you're getting Sita, Gita, Rahi. So Sita is the mother of Gita, Gita is the mother of Rahi. All I wanted to illustrate was how you can have multiple. Similarly, Sita, Anita, Raj is another combination. So Sita is the mother of Anita, Anita is the mother of Raj. Sita, Anita, Smita also works because they're step siblings. Right? That's it. So you can see, you see this, right? It's a very powerful way to get information. For information retrieval, you can use this in a very powerful way. So notice that here we understand the domain pretty well. So once you understand the domain, this is a very nice way to model it. And lots of queries that can be asked can be converted into simple Prolog queries or Prolog goals and answered. Okay, are there any questions about how this works? I mean, the basic thing. We'll go into details later about exactly how it does things. But for the moment, how it. Any questions on the programs? Okay, so if that is clear, then let's go to back to this. So we were looking at this earlier. We saw what programs are, right? We saw their facts and rules, and when you want to execute so once you define the facts and rules, you have in some sense modeled the domain, and you can model complex domains. It requires a fair amount of creativity to model it. Yeah, yeah. Information retrieval is the obvious thing, but yes, you can do. We said it is Turing complete, so you can do any calculation that is real language in Prolog. Right? It may not be as easy to do or everything. You obviously won't use Prolog to solve systems of linear equations. It's not meant for that. But it's not the case that you can't do it. You can do it. The whole thing will be much more difficult to express. We will see later on, right? We saw lists, so we'll see that you can do various kinds of standard algorithms also. So maybe in the next class, when we're going to look at lists, we'll see that there are various ways of doing things. And some of them are quite insightful actually. Okay? So notice that in our code, when we wrote code here, notice how smoothly we did recursion. Take for example ancestor here. Okay? If you look at ancestor definition, notice that it's a recursive relation, right? So we are saying this is the base case ancestor x y. If x is the parent of y, then x is an ancestor of y. And then we have the recursive relation, right? If x is an ancestor of y, if z is a parent of y, and x is an ancestor of z. So recursion is so smooth here. I mean, it is so natural. And that's pretty much how we'll do a lot of recursion. Iteration will also be done pretty much using recursion, has to be done using recursion. Okay, so we saw this. Now let's move ahead. So, so there are variables in Prolog, right? We saw variables everywhere. We saw variables in rules. We saw variables in the goal. Now, when you are looking at variables in the Prolog program, okay, the Prolog program is just the facts and the rules, not the goal. Then all the variables are to be interpreted as universally quantified, because in a fact there is no variable. In a fact, there is always a constant. So you are asserting something about a specific, specific object that has been instantiated. It's not a variable. In a rule, all the variables are universally quantified. So you are saying for all x, y, z, whatever, that if the condition holds, then the conclusion holds, the head holds. If the body holds, then the head holds. That's what you are asserting. So the variables there are all universally quantified. When you are asking a question, that is when you want to execute a program, then you are really saying, does there exist? Because you are asking for an instantiation. So when I said something like, for example, I said, let's say I said, grandmother Sita X, right? This was one of our queries here, remember. Did you see this? Yeah, here. So we said grandmother Sita X. So what is being said here is that find me all instantiations of X. So find X, right? Or equivalently, does there exist an X such that Sita comma that X, specific instantiation of X, is true? So what you are essentially saying in that case is this, right? So you're saying, does there exists X such that grandmother Sita X is true? Now what is actually happening is that, how can you prove this? So you have a theory. The theory is your Prolog program. So let's say P is your program. So this is your theory, or equivalently what you are calling model of the domain. Okay. Now using this theory P, you want to prove the goal. You want to prove the goal G. So you want to say, if all of this is true, then is this true or not? You expect it to be true. Now G can have variables, right? For example, here X is a variable. So the question becomes, does there exist an instantiation or a binding for X such that it is true, given P is true? So one way to do that is the following. You take P, you add to it the negation of the goal, okay, and once you have, if indeed G follows from P, then if you add the negation of that, then essentially what you are saying is your your whole thing P plus not of G is a contradiction, right? So what you are doing is you are doing a proof by contradiction. So what you are adding is the query. The query is, there exists an X grandmother's this thing. You have to negate it because you have to add the negation of that to the program. So what you do is you add the negation of that. So P union negation of G. G is there exists, so it's negation of there exists X grandmother. Let me just write it as Gn, Gn Sita X. Okay. Now those of you who have done logic, you know that you can convert this to for all X not of grandmother Sita X. So it's saying find me all the bindings for X such that for all X, it should be the case that Sita is not a grandmother of that. Right? I add that if I am able to derive a contradiction, then I will be able to argue that G is true. Right? It proves by contradiction. You add the negation of the thing you want to prove, show that it is leads to a contradiction, therefore G must be true. That's exactly what a theorem prover does. It's called a resolution theorem prover or a refutation theorem prover because you are refuting things. So P is the theory. You want to prove G from the theory. You add the negation of G to the theory and show that it leads to a contradiction. Okay? How exactly this happens and the theory, little bit of the theory behind it, we will discuss independently. First, I want you to understand, this is what's happening at the back. So all Prolog programs work this way. So that's why it's declarative, right? So if you look at the declarative meaning of a Prolog program, so actually a Prolog program has two kinds of meanings. One is the declarative meaning. The declarative meaning is just the set of facts and the statements, the rules, right? So facts are like concrete data, which is true. Rules are like general rules, that is, they hold for all instantiations of the variables that are present in the rule. Okay? And the ordering of the body, etc., does not matter. The ordering of the facts and rules does not matter because it's a logical thing. It should all hang together. Right? So whether the rules are coming first or the facts are coming first, all these things don't matter when you're looking at the declarative meaning of a Prolog. All that's being said is that the rules and facts together are a set of assertions. The ordering does not matter. Right? The other thing that is important is Prolog makes what is called the closed world assumption, which means that only what is given there is assumed to be true. You can't say anything about something that is not asserted. So it's called the closed world assumption. So only the assertions made in the program P are assumed to be true. So what is the declarative meaning of the program formally? So the declarative meaning of the program P and a given goal G is true if and only if exists a clause C. So clause C can be either a fact or a rule in P for which we can find a substitution S, which means all the variables which are present in the clause or equivalently in the goal giving an instance I of clause C such that the head of I is the same as G after substitution and all predicates in the body are true. So what you're doing is you're going to start with that grandmother. Look at the head of grandmother. So for instance, if you look at this, grandmother is here, right? So it's here. So your goal was grandmother Sita X. Okay? Now notice that these variable names X and all those clashes don't matter because they are for us they are variables. The variable names are sort of defined apart inside the system. So the X I put in the goal is not the same X as this. So basically the thing that I put here was Sita. So X gets bound to Sita. Y gets bound to X, right? Because that's what I put here. So Sita is the first argument, X is the second argument. So grandmother matches, I try to match it with a grandmother on in the set of rules or facts. So I don't have any grandmother fact, but a grandmother rule is there, so I see if it can be matched, right? And matching means can it be instantiated properly. We'll see exactly what the matching algorithm is next class. But you can see intuitively that if X has the value Sita and Y and X are made equal, So this is something where both are variables. So they should, all it is saying is that both of them should have the same value. So if you can substitute y by x or x by y, it doesn't matter. So you can substitute, let's say, this y by this x. Then this will be true, right? And this will be true exactly when the right hand side is true. So now grandparent x, so this x is theta, so you're again asking this x and is a grandparent of y. This y is again a variable here, so it is this x, okay, not this x and this x are different, so maybe we should call this z. That will clarify things. Okay, so here it is, y is substituted by z, this y becomes z, and it is asking is female z, so it has to first do this. Well, notice the order doesn't matter, but in practice one of them will have to be done first, the second one will have to be done next. So declaratively it doesn't matter whether I check female x first or female z in this case, since x has been substituted by theta, so female theta and grandparent theta comma z. Okay, so I will go to grandparent, then this will take me to parent, and so on. So you can see how this whole thing goes. Okay, this whole thing basically keeps trying to match things and tries to see if a match exists, then instantiates it, goes back and tries to prove the right hand side true, and keeps repeating this process until the whole thing has been worked out. That is, you have a binding for the necessary variables, and that is exactly what is happening. We'll see some. We'll see how this whole process goes by actually looking at an execution trace. But you can sort of get an idea, intuition about what is.